Hello, my name is Rob Reynolds. Welcome to Mat-073. Today we're going to be looking at our second section, 8.2, exploring composite functions and looking at inverse functions as well. Composite functions are f at g at x. Sometimes it's denoted f of g at x, but I would immediately write it as f at g at x. And then inverse means every time you see an x, write a y, and every time you see a y, write an x. So inverse composite functions is where we're going to start first, and that's a function within a function. And again, this looks like f times or g of f. This little symbol right here is pronounced of. It's not a multiplication symbol. So what it literally means is if you were to take a 1 and throw it in here, 3 times 1 plus 1 is the 4. And then the 4 goes into the next function. So half of 4 is 2. 2 minus 3 is negative 1. And you can continue doing that. So it's really an operation of two functions, one function within the other function. So again, this is read the composite function. It says f and, f is composed, or f circle g. I wouldn't pronounce it any of those ways. I would say either f of g or f at g. And I like kind of at because that's kind of telling you exactly, at that particular x value, where's the function's y value. So again, this is just notation that you need to be familiar with. If ever you see f of g at x, I would immediately write yellow as pink. I think that will make a little bit more sense. So you can see you do the inside function first, g at x, find that value, and then plug it into the f at x. Maybe it'll make more sense if I show you an example here. So I'm going to rewrite part A as f of g at x. So that means f at g, and they're telling me the x value is 4. So if I were to do the inside function first, it says go to the g function and plug in a 4. Well, here's the g function. 4 squared is 16 plus 2 is 18. So f at 18, now we go to the f function and plug in an 18. And 4 times the 18 gives me the answer of 72. Let's try this again. Let's try g at f at 4. G at f at 4 is probably not going to be the same thing as f at g at 4. We'll explore here. This, first of all, says, let's go to the f function and plug in a 4. So I'm going to come here. This time I'm starting with 4 times 4. So that's going to give me g at 16. And now this says go to the g function, which is right here. And instead of doing x squared plus 2, I'm going to plug that 16 right in here. So 16 squared plus 2, I'll bust out my calculator, and that'll be 258. So you can see these are not equivalent to each other. So if I generalize this in just terms of x, this says f at g at x. So the g at x function is right here in yellow. That's my x squared plus 2. Now that says go to the f function, and instead of writing, here it is, instead of writing 4x, we're going to replace x with parentheses, and then in those parentheses, which is my old x value, instead of 4 times x, I'm going to do 4 times the g function, which is x squared plus 2, and I'll probably just simplify this by distributing the 4x squared plus 8. The last example goes the opposite direction, g at f at x, and the f at x function is 4x, so I'll write g at 4x. Now this says go to the g function. Oh, here it is in yellow again. But instead of writing x squared plus 2, that's the whole g function, I think the trick is to replace x with parentheses. So instead of x squared plus 2, we'll write parentheses squared plus 2, and then in the parentheses goes that 4x, or whatever value that you can have to plug in for that. So in this case, it's going to be 16x squared plus 2. And once again, you can see that f at g at x does not equal g at f of x. Sometimes it does, and if it does, then they're called inverse functions, and we'll get to that in a moment. So here's how the author chose to work these out. Those are the first two examples, and then here are the generalizations. So that, well, I think what they want you to see is f at g at x does not always equal g at f of x. If it does, it's a special function which we call an inverse function. And so that's what we're going to talk about next. These inverse functions means every time you see an x, you're at a y, and every time you see a y, you're at an x. So it literally means instead of the point x comma y, we're going to flip this to y comma x, but this, our old y value becomes our new x, and our old x value becomes our new y value. So really I shouldn't call this yx. This is still just xy, but that's xy on the inverse function. So you can see that the inverse function, instead of plotting the point, here it is 3, 7, you're going to come down here to 7 comma 3. Now notice if you do that for all of the points, you'll have this nice line of symmetry, and that line of symmetry will always be at y equals x. So if you were to fold this left side, or this pink side, over that line, it would fall onto the yellow side, and it would have symmetry, which means all the points on the yellow side would fall onto the pink side. So let me give you an example here. Here's a function. If I find its inverse, every time I see a x, I'll write a y, and every time I see a y, I'll write x. Usually functions are defined in terms of y, though, so we need to solve this for y. And in order to do that, we'll need to complete the square. I'm going to get a positive 1 term here first by multiplying through by -1, and reorganizing some terms a little bit here. So if I complete the square by taking half of the middle term and squaring it, I can complete the square by adding 4 to both sides. So that'll give me -x plus 4 is equal to, and then this is now a perfect square. So if I were to factor this yellow, it really factors to x minus 2 quantity squared. So just, oh, excuse me, that's a y. Y minus 2 quantity squared. So if I were to take the square root of both sides, which gives me plus or minus x plus 4 equals y minus 2, here comes the inverse function, which is, this is notation for inverse function, plus or minus the square root of -x plus 4 plus 2. So to graph this, I could go to my calculator, and under the first y sub 1, I'll put the 4x minus x squared. That's the first function. And on the second one, I have to do the positive square root of -x plus 4 plus 2, and the negative square root of -x plus 4 plus 2. I need a negative in here, so sorry. So I need a positive and a negative. So I'll hit second delete, which is an insert key, insert the negative, and let's see if it graphs it. So the blue is the first function, the red is the positive square root, and then the black is the negative. So I got a plus or minus square root. So it looks like 3 functions, but it's really just 1. If you want to see a table setup of that, I'll hit second graph, and I get instant t-charts of some points that we can graph. But basically, it looks like this. If you just would have found points off of this by doing a t-chart, for example, you plot the point -1, -5, which is right here, -1 comma -5, and you find that's inverse. Well, the inverse of -1, -5 is -5, -1, which is down here. So you can see this red point comes over here, and you can see that that's that nice line of symmetry. So if I were to fold that over, point A would fall onto point B, which is -5, -1 right here. So this inverse is down here. And we could continue with the chart. So really I only needed to find points on the function because the inverse of 1 comma 3 is going to be 3 comma 1. So looking at whether a function has an inverse or not, and if the inverse is a function as well, we could look at 2 examples here. The states and toys, if you were to flip these around and go backwards, are the inverse as a function? Well, in order for it to be inverse, every x has to only go to 1y. And Jim here is going to ropes and going to phone, and that's violating. So toys is not, the inverse of the toy function is not also a function. But if both graphs, the original function and its inverse, are both functions, it's called a one-to-one function. And you can test to see if something's a one-to-one function by the vertical line test. And the vertical line test says if it only crosses the function once at one point, then it is a function. But also test the horizontal line test. No matter where I draw a horizontal line, it also crosses once. So that's called a one-to-one function. So look at this. This is not even a function because it doesn't pass the vertical line test. This passes the vertical line test and it passes the horizontal line test. So this is a one-to-one function. And this would be a one-to-one function. So if it passes both, so here's an example where it passes the vertical line test, but it does not pass the horizontal line test. So it needs to pass both tests in order for it to be a one-to-one function. So this is not a one-to-one function. So looking at this, let's go ahead and quickly graph x squared plus 1, which means it's a parabola, but it's moved up 1 unit. It passes the vertical line test. Sure enough, it's a function, but it does not pass the horizontal line test. So I would say not a one-to-one function. They're asking, is this a one-to-one? And I would say no, it's not a one-to-one because it doesn't pass the horizontal line test. So inverse functions, again, notation for inverse is f to the negative first. That looks a little deceiving because x to the negative first is the reciprocal. Be careful, this is just a notation nightmare. This is not true. You don't, this blue guy here means reciprocate, but if it's, but that's only if it's a number. If it's a function, it means find the inverse, which means every time you see an x, write a y, and every time you see a y, write an x. So determine whether it's a one-to-one function. Well, this is going to be a line, and all lines, it's starting at -2, rise 1, 2, 3, 4, 5, run 1. So the inverse of this, we can just check really quick. You bet it passes the vertical line test. It also passes. So determine whether it's a one-to-one. Yes, that means not only does the vertical line test pass, but the horizontal line test pass. If it is a one-to-one, find the formula for the inverse. Well, remember, f of x is really just y. So the formula for the inverse says, let's replace x's for y's and y's for x's and solve for y. So the inverse, if I divide everything through by 5, is 1/5 x plus 2/5. And I'll replace y with the inverse function so you don't get that confused with the original y. And then it says graph both inverses. Well, it's hard to graph 2/5, but I can get close. 2/5 is a little bit above 0, and then rise a full unit and run 1, 2, 3, 4, 5. So it looks like this. But remember, the most important thing is when all is said and done, if you've done this correctly, you should have that nice line of symmetry about y equals x. And this is close. So there's the solution for A. There's B, and then and C. So this one says graph not only the line, but also graph the inverse. And I think we just did that. So there's the solution for the last one. So that's kind of what I had here. So remember, inverses have this nice line of symmetry about y equals x. It doesn't matter what the function looks like. I could always replace any point. So if this is xy, this point down here would be my y comma x. I'm just replacing those values. So remember notation, I would replace this of symbol with composite function notation. So if f at g at x equals x and g at f of x also equal x, then that's a nice proof that they are inverses. So let me show you what I mean here. If we find f at g at x, and we work through this, and that equals x, and we look for g at f of x, and we work through this, and that also equals x, then we can say that f at x and g at x, I'm going to let this be g at x instead of the inverse function, because sometimes you don't know if it's a g at x. So I'm going to replace the inverse function with just another function called g at x, and we're going to test. So this says let's plug the g function in, which is x plus 1 divided by 3. Plug that into the f function. So again, I'm going to go to the f function, and every time I see an x, instead of writing 3x minus 1, I'm going to plug in that value. So again, I think the key here is to replace x with parentheses. This proof will look a little bit different. If I cancel this, this is x plus 1 minus 1, and sure enough, that equals x. So the left side should look different from the right side. Let's go find out. The f at x function is 3x minus 1. So this says go to the g function, which is here, or here, and let's not write x plus 1 divided by 3, but let's go plug in, again, replacing x with parentheses, I think is the key here, even if it takes another step to write this. So this is really 3x minus 1 plus 1 all divided by 3, which is really 3x divided by 3, and that cancels to x. So again, the left side looks a little different than the right side, but the results are the same. Here's how the author worked through that last example. The important thing is your conclusion. Yes, you're proving to me that these are inverses, because when you check the composite functions, then they both equal x. If you have any questions, feel free to email me.